We're going to take a look at presynaptic modulation. Presynaptic modulation is going to involve a different type of synapse than what we've been talking about before. So it's going to involve these axo-axonic synapses. So if you look at the word axo-axonic, we're going to be having the axon of one neuron synapsing with the axon of the other neuron. So that's an axo-axonic synapse. And that's really different from the axodendritic synapse and the axosomatic synapses that we've been talking about. So remember, those types of synapses, when they release their neurotransmitters, they're going to create some graded potentials, some EPSPs and IPSPs in this postsynaptic neuron. But what's going to be happening at this axo-axonic synapse is we're not going to be creating any graded potentials at all. So what's going to happen is neurotransmitter will be released at this axo-axonic synapse, and a lot of times the neurotransmitter will end up binding to, for example, maybe a G protein linked receptor, and it's going to affect the voltage-gated calcium channels that are in the axon terminals. So remember, we've got those voltage-gated calcium channels that when they open, they let calcium into the axon terminal, and that's going to cause the exocytosis of the vesicles that are storing the neurotransmitter and cause the release of neurotransmitter into that synaptic cleft. And then the neuron can then talk to whatever the postsynaptic cell is on the other side. So what's going to happen with this axo-axonic synapse is that it's going to affect how much of this neurotransmitter gets released. Okay, so there's two ways that we can affect things. We have presynaptic facilitation. And facilitate means to help. So presynaptic facilitation means that at this axo-axonic synapse, when you release the neurotransmitter there, you end up increasing the amount of neurotransmitter released by this presynaptic neuron, and then you're more likely to create a bigger EPSP in this postsynaptic neuron and then reach threshold and send the signal on in that postsynaptic neuron. And then the other way we could get presynaptic modulation is presynaptic inhibition, where this axo-axonic synapse releases neurotransmitter and we end up decreasing the amount of calcium coming into the axon terminal, and that will decrease the amount of neurotransmitter that's released by this presynaptic neuron. And so that means if you're releasing less neurotransmitter, you're going to create a smaller EPSP, and then you're not as likely to reach threshold and not as likely to generate an action potential and send the signal on. So that would be inhibitory. All right, so let's take a look at some pictures here. All right, so this is just showing you this modulating neuron is what we end up calling this neuron that's forming this axo-axonic synapse. So here's our axo-axonic synapse. And this neuron here is our presynaptic neuron. And the neuron afterwards here is the postsynaptic neuron. So just some terms there. All right, so let's take a look at some pictures here. So we've got our presynaptic neuron, and that's C, and our postsynaptic neuron is X. And X is what we're going to be measuring our graded potentials and see if we reach threshold and get an action potential at the axon hillock. Okay, and the neuron E, that's our modulating neuron. That's the one that's going to be forming this axo-axonic synapse with our presynaptic neuron C here. Okay, And we're going to be looking at presynaptic facilitation first. Remember, facilitate means to help. So E is going to help presynaptic neuron C release neurotransmitter. So it's going to increase the amount of neurotransmitter that gets released. Okay, so if we have presynaptic neuron C just firing and releasing neurotransmitter by itself, here's how much neurotransmitter it releases. And maybe it binds to some ligand-gated ion channels that are specific for sodium, let some sodium into the postsynaptic neuron X here. And we create this EPSP, but it's not big enough to reach threshold. We don't get an action potential produced. But if we have E firing and releasing neurotransmitter at the same time that C does, when E releases neurotransmitter, it actually will increase the amount of calcium coming into the axon terminal of C, and that means you can release more neurotransmitter from C. So that's presynaptic facilitation. So presynaptic facilitation, you're going to increase the amount of neurotransmitter released by this presynaptic neuron. And so if we look at C and E firing at the same time with presynaptic facilitation, you can see by increasing the amount of neurotransmitter released by neuron C, we can get a bigger EPSP produced by in the postsynaptic neuron X, and we reach threshold at the axon hillock, and we can produce an action potential in neuron X, and then that gets sent down to the axon terminal in X. Okay, and then just the opposite would be presynaptic inhibition. So here's our presynaptic neuron F, and if F just fires by itself, here's how much neurotransmitter it releases, and it produces an EPSP in our postsynaptic neuron Y, but it's not enough to reach threshold. We don't get an action potential. Okay, and then H, if it fires and releases neurotransmitter at the same time as the presynaptic neuron F is firing and releasing neurotransmitter, H will actually decrease the amount of calcium coming into the axon terminal of this presynaptic neuron F, and that will decrease the amount of neurotransmitter released from this presynaptic neuron F. And so this is presynaptic inhibition. You're going to decrease the amount of neurotransmitter released by F. So you can see that if you have F and H firing at the same time, you're not going to get very much neurotransmitter released by F, and so you're not going to get much going on in the postsynaptic neuron Y. Okay, and so that would be inhibitory. You're not going to reach threshold. You're not going to get an action potential. Okay, all right, and then just a little quiz here. If we have neuron F and G firing at the same time, and F and G both produce EPSPs in postsynaptic neuron Y, what kind of summation is that if you have F and G both firing at the same time? And you would add their graded potentials together, you reach threshold, and you get an action potential with F and G both firing together. So hopefully you said that that's spatial summation if you have F and G firing together. So just a little review there. Okay, let's look at a real-life example of presynaptic inhibition. So let's say that you've got a soldier who's in a battle and he gets shot in the leg. But the brain realizes that we're in a battle, this is a life or death situation, and the brain says we gotta ignore the wound in the leg because we got to keep fighting because otherwise we're going to be dead. Okay. So the brain has a system called the descending analgesia system. Okay, and analgesia means pain relief. So what we've got pictured here is we've got this sensory neuron coming up from the leg into the spinal cord, and this inner neuron is just a nerve that's going to be taking the pain signal up towards the brain to let the brain know that, hey, we got shot in the leg and that really hurts. And the brain says, well, I want to block this pain signal coming from my leg because I need to ignore that right now because I need to keep fighting. Okay, because otherwise if I pay attention to my leg, I'm going to get killed here. Okay, so the brain is going to send some signals down some other neurons, and these neurons will travel down the spinal cord, and they're going to synapse here on this sensory neuron that's bringing this pain signal from the from the leg. And what kind of synapse is going on here? So would this be an axodendritic or axosomatic, axoaxonic synapse? So hopefully you recognize that that's an axoaxonic synapse, right? You've got one axon here, and then you've got this axon terminal here, right? So this would be an axoaxonic synapse. And so this is going to be presynaptic inhibition that we're going to be doing. And so this neuron is going to release a neurotransmitter. It's called enkephalin. And enkephalin is actually a natural opioid, a natural painkiller that your body produces. And so this neurotransmitter will bind to some opioid receptors, and they will decrease the amount of calcium coming into this axon terminal, and that'll decrease the amount of neurotransmitter that's being released by the sensory neuron that's trying to tell your brain that, hey, you got shot in the leg and it really hurts. And so you're not going to get as big of graded potentials, as big of EPSPs in this neuron that would normally take those pain signals up to the brain. And so you're going to be blocking those action potentials from being formed. And so you don't form those nerve signals, and you block those nerve signals from even being generated in the spinal cord. And so those pain signals don't get sent up to the brain, and so the brain doesn't feel that pain from your leg. And so that allows you to keep fighting in the battle, ignore the pain in your leg. But then after the battle is done and you survived, then the brain says, oh, I guess we better take care of our leg. And so the brain will stop sending signals down to the spinal cord and stops releasing that enkephalin. And now we're going to let those pain signals from the leg through and let the brain know how bad the leg hurts, okay? Because then you need to go take care of that. So that's presynaptic inhibition, and you may have experienced that at some point, you were hurt, but you were in a stressful situation and you had to keep going, and your brain has the power to block those pain signals, to, keep going and get you out of that stressful situation. And then once you're out of there, then it says, okay, we'll let those pain signals through. Okay, so you may have experienced that. So that's presynaptic inhibition. So that's pretty cool.